Hey everyone, today I want to begin with this warm-up problem as a quick review for a particular type of problem that was commonly missed on the quiz from last week. So here we're converting a point that is in rectangular form into polar form, and we want it so that the r value in polar form is positive and that the angles between 0 and 2 pi radians, okay? So if we're in rectangular form, we know that the point that we are given, this represents an x coordinate and a y coordinate, right? And we can find the associated r value in polar form by simply using x squared plus y squared equals r squared. Most of you did this part correctly on the quiz. So x squared in this case would be 0.64, y squared would be 4.41. That, of course, adds to 5.05, and then we'd square root both sides. I'd round here. Let's do 2.247 approximately. Okay. Now, where many of you went wrong was on your angle theta. So we can always initially find theta by using the inverse tangent function, right? Since we're given the x and the y values for the rectangular set of coordinates. So I would find inverse tangent of negative 2.1 over negative 0.8. And sometimes this is enough, but what you have to understand and recall is that the inverse tangent function, it only yields quadrant 1 and quadrant 4 angles, okay? Here we're taking inverse tangent of a positive value, so this represents quadrant 1, okay? But if you go back and you look at the original points in rectangular form, a negative x value and a negative y value means we're actually in quadrant 3, okay? So that means we need to adjust the inverse tangent function here to give us the proper quadrant for theta. To do so, I just need to add pi to it. So this is where some of you went wrong on the quiz. You didn't add that pi, all right? If I find inverse tangent and then I add pi, I should wind up with 4.348 in this case. So my point is 2.247 for r, 4.348 for theta. All right, just wanted to clear that up in case you missed that last week. All right, we are going to move into section 2 today, where we are going to be graphing various types of polar equations. There's a lot of different types of equations that we'll focus on in this particular section. You can get some really unique, interesting looking graphs when you're in polar form, okay? But today we're just going to focus on graphing lines and circles when they're in polar form, okay? So click to example 1, and I have 3 different equations here, okay? So let's just start with r equals 4. Before I graph each one of these, I'm going to convert them from polar form into rectangular form so you can have a better understanding of what their graphs are actually going to look like, okay? So r equals 4. To get this one into rectangular form, all I need to do is square both sides of the equation. Okay, r squared is x squared plus y squared, and then of course 4 squared is 16. So that should look really familiar to you now in rectangular form. This is nothing more than a circle centered at the origin, whose radius is the square root of 16, or 4. Okay? So really all we're working with here is a circle of radius 4 centered at the origin. Now, how do I graph that in the polar coordinate grid? Well, remember, each one of the circles in the grid has an r value associated with it. So the smallest circle in this grid would be r equals 1. Centered at the pole or at the origin. Then the next circle would be r equals 2, and so forth, okay? So for us, r equals 4 would be this guy. kind of hard to draw. Just do the best you can there. There we go. Okay. Next equation we're going to graph is theta equals pi over 4. And in order to get this one into rectangular form, I am going to take the tangent of both sides of the equation. And the reason I do that is because tangent of theta we know is defined to be y over x. So right there's a conversion into rectangular form. And then tangent of pi over 4 is simply 1. Okay. Now we're in rectangular form, but probably helpful if I multiply both sides by x to clear this fraction, and notice what I end up with. Y is equal to x. This is nothing more than an equation of a line whose slope is 1 and whose y-intercept is 0. Okay? All right, so the question becomes, how do I graph something like this when I'm in the polar coordinate system? So not only do you have the circles in the grid, but you also have the lines, right? And each one of those lines represents a different angle measure. So like right here represents 0 radians. This is pi over 12 radians, or 15 degrees. 2 pi over 12, which is pi over 6. And then right here is pi over 4. Okay? And that's the one that we're after in this case. So a lot of times what I get from students is they only end up drawing the line looking like this. Okay? And what we need to understand here is technically the line needs to extend in the other direction as well. I think the reason that sometimes students don't extend it in the other direction is because this is typically labeled as 5 pi over 4, which doesn't match the theta that is in our equation. But here's where you have to understand how to plot points whose R values are negative. Okay, so for example, let's say I wanted to plot the point negative 2 pi over 4. Okay, so we would sweep out the pi over 4. It would take us on the terminal side of the angle for pi over 4. But then because R is negative, we'd have to extend in the opposite direction of that terminal side, and it would take us over to here, right? So even though that side is labeled as 5 pi over 4, we can still use it to plot points whose angle measure is positive pi over 4, provided there's a negative R value. Okay, so probably making that into a big deal, but just understand whenever you have theta equals an angle measure, it's going to represent a line extending in both directions. Okay. All right. Next, we have R equals 2 over sine of theta. All right, and I'm going to rewrite that like this. And this one's pretty simple to get into rectangular form. Just multiply both sides by sine of theta to clear that fraction there. You end up with R times sine of theta is equal to 2. And we know R sine of theta is the same as y. Y equals 2. Okay? Now we're in rectangular form, and we know that represents a horizontal line, right? Okay, so now the question becomes, how do we graph a horizontal line in the polar coordinate system? Well, the line is just going to look tangent to the circle whose radius is 2, okay? What we have to understand is that the circle of radius 2, it technically would intersect the coinciding y-axis at the point of, it would intersect at the point of 0, 2, okay? So that's the point of tangency between the circle r equals 2 and then this line of r equals 2 over sine of theta. And it's just going to look like this. Okay? All right, now let me throw one more quick one at you here. Let's say I had r equals 2 over cosine of theta. Well, similarly, multiply both sides by cosine. You end up with r cosine equals 2, or x equals 2. And that would be a vertical line. So what's that look like when I graph it in the polar grid? Well, now it's going to be tangent to the circle r equals 2 at the point 2, 0, which would be right through there. Okay? All right, last thing I want to talk about real quickly in this lesson is symmetry within the graphs of various polar equations, okay? So these are some generalizations to make that are going to help us in the coming days, all right? Whenever I'm graphing polar equations of the form r equals, and the other side of the equation has a sine of theta in it, so for example, r equals 4 sine of theta, I can tell that the graph is always going to be symmetric with respect to theta equals pi over 2. Now we just learned something of the form theta equals pi over 2. That just represents a line. So in this case, it would be the line that coincides with the y-axis. Okay, so notice that circle represented by r equals 4 sine of theta, it is in fact symmetric with that blue line I've drawn in. Now let's say we had cosine on the other side of r equals. So for example, r equals -2 cosine of theta. Here the symmetry is going to be with respect to the polar axis, which is the same as the line theta equals 0, and that coincides with the x-axis of the rectangular coordinate system. Okay, so you can see that circle graphed here is in fact symmetric with that line. All right, now a little bit more on each one of these equations. So we're winding up with circles from each of these. Notice we got circles back here in part A where we had r equals 4. The difference is when it was just r equals a constant, the circle was centered at the pole. Now, if I bring in sine or cosine of the angle theta, multiplying that constant, then I end up moving the center, okay? So let me show you how you can reason this out in rectangular form. So r equals 4 sine of theta. I'm going to multiply both sides by r on this one, okay? If I do that, that's going to lead me to r squared equals 4r sine of theta. R squared can convert to x squared plus y squared. And then over on the right side, 4r sine of theta is the same as 4y. Now you're in rectangular form. Doesn't mean a whole lot to me though in the current state. So I'm going to manipulate this. I'm going to move 4y to the other side by subtraction. And then I'm going to complete the square. Okay, I use the -4, that's the coefficient on y. Half of that's -2, square it, you get 4. That's your add in to each side to maintain balance. Now that's a perfect square trinomial, and it will factor to y minus 2 squared. And then hopefully that looks a little bit friendlier to you. This is a circle centered at the point 0, 2 in rectangular form, whose radius is 2. And notice that does match the graph that we have here. This would be the coinciding point of 0, 2 in rectangular form, and you can see does in fact that circle have a radius of 2. Okay. Similarly, for this equation, r equals -2 cosine, I could multiply both sides by r again. R squared becomes x squared plus y squared. -2r cosine becomes -2x. Let's add that to the other side. I'll put my blanks in for completing the square as well. And End up needing to add in a 1 to both sides. X plus 1 squared plus y squared equals 1. And you can see that this is another circle centered at the point of -1, 0 with a radius of 1. Okay? With a radius of 1. All right, so notice how that matches my graph here. Right there's the coinciding point of -1, 0, and it does in fact have a radius of 1 unit. Okay, so now you can see that anytime I'm working with r equals a constant multiplied by either sine of theta or cosine of theta, that ends up being a circle just with the center shifted either left, right, up, or down. Okay? All right, that's it.